of fragments retain the same characteristic shape. Okay. The properties of solids can be explained at the atomic level. Okay. Level. Okay. In terms of definite and regular agreement of the tiny invisible individual particles that makes up the solid. Okay. This arrangement is called an error or a crystal lattice. The tightly packed particles are held together by attractive forces. This is the motion of the particles in a solid. Only a slight vibration within the crystal lattice. Okay, structures of several crystalline solids are discussed in great detail in chapter 13. Okay. Unlike solid, liquids take the shape of their containers, except for generally flat surface at the top. Like solids, however, liquids maintain a nearly constant volume. If you have a 12-ounce soft drink, okay, you have 12 fluid ounces, whether the soft drink is in a can, in a bottle, or spray out in a puddle on the floor, okay, which demonstrates another properties of liquids. Unlike solids, okay, liquids flow, but some liquids flow more readily than others. Okay. Now we know water and alcohol are two liquids that are miscible. Okay. This means that they will dissolve in one another. That is, they can be mixed in any proportion and remain mixed without separating into layers. Okay. Vegetable oil and water are two liquids that are immiscible. When shaken together, two immiscible liquids form a cloudy mixture, okay, with tiny droplets of one liquid visible suspended in the other. If all of the two stand, the immiscible liquids separate into two distinct layers. Okay. Individual particles in a liquid are close together, and the material attractions are fairly strong. Yet they are free to move about. Solids and liquids are virtually incompressible because the individual particles are closely spaced. Okay. Now gases. Gases don't have a definite shape or volume. Okay. Unlike solid and liquid. Okay. Don't have a definite shape or volume. They take the shape and volume of the container they occupy. Gases expand to fill completely whatever container they occupy, but they also can be compressed into smaller containers. Okay, gases also diffuse rapidly. That is, they mix with other gases as they move to fill the available space. At the atomic level, visualize the particles of a gas moving independently of one another. Moving independently of one another, with much space between the particles. Okay, there are much space between the particles. Okay, unlike the solid and liquid. Okay, now we learn this example. States of matter. Identify the physical state of each is this at room temperature and room temperature. Okay. Oxygen, water vapor, candle wax, alcohol. At room temperature, we learn oxygen and water vapor. Okay. Are gases. C. Candle wax is solid. Alcohol is liquid. Okay. This question is very simple. Okay. Now we learn the elements and compounds. And we know these words are the chemical words. Okay. Chemical words. Okay. We know what is the pure substance. Okay. In chemistry, a pure substance is a single chemical composed of the same kind of matter. Okay, only one kind of matter with the same kind of particles throughout. Okay, it can be either an element or a compound. Okay, now we learn what is the elements. Elements are the most fundamental substances from which all material things are constructed. The smallest particle that retains the property of the element is an atom. Okay, the smallest particle is an atom. Okay, this particle retains the property of the element. Atoms of a solid element are arranged in a regular pattern and are of the same type. Okay, of the same type. What is compounds? Compounds are pure substances that are made up of two or more kinds of elements combined together in fixed proportion. Okay, in fixed proportions. Each compound has a chemical formula. That indicates the ratios in which elements are combined. Properties of compounds are different from those of the individual elements involved. Okay. Now we learn the general liquid. Okay, this is a simple compound. Okay, water was once thought to be an element. Okay, but now we know it to be a compound. Okay, not an element. This compound composed of two elements, hydrogen and oxygen. The chemical formula for water, H2O indicates, okay, this chemical formula indicates that two hydrogen atoms are combined with each atom of oxygen atom. In a label, water can be decomposed into hydrogen atoms and oxygen atom. Each compound has a specific atom ratio and a specific percentage by mass for each element in the compound. This is a statement of the law of definite composition, which is also called the law of definition proportions. Okay, now we learn the distinction between elements and compounds. Okay, now explain how the compound solid chloride is easily distinguished from the elements. Okay, solid elements atom and chlorine atom. Okay, the elements that were combined to make compound. Okay, we learn the element solid and element chlorine. Okay, are the two elements to combine the table salt. Okay. Uh, so we can explain it. Sodium chloride, okay, is a table salt, okay, is a table salt. Okay, it is a white creatinine compound, white compound, okay, used in seasoning. It dissolves in water, okay. The elements, solid and chlorine, look nothing at all like the compound. So sodium is a soft metal, okay. Silvery reactive solid metal is a soft metal, okay. Sodium is a soft metal. Chlorine is a gas, okay. Poisonous gas, a pale greenish yellow poisonous gas. Okay, we know. Okay, the elements sodium and chlorine look nothing at all like the sodium chloride. Okay, now we learn the part four. Pure substances as mixture. Okay, pure substances and mixture. Okay. Any sample of matter can be classified as either a pure substance or a mixture. Okay, so we know we can identify what is a pure substance, what is a mixture. A pure substance can be either an element or a compound. So a kind of element or a kind of compound may be a pure substance. The composition of a pure substance is definite and fixed. The composition of a pure substance is definite and fixed. Okay, the composition of a mixture may vary. Pure substances are either elements or compounds, and the mixture are either homogeneous mixtures or heterogeneous mixtures. Okay, we can learn the prefix okay, homo and hetero. Okay, so we learn these two kinds of mixture. Okay, homogeneous mixtures and heterogeneous mixtures. A heterogeneous mixture doesn't have uniform properties throughout. Okay, heterogeneous. Okay, the composition of one part or phase differs from the composition of another part or phase. For example, an oil and water mixture is an example of a heterogeneous mixture. Okay, heterogeneous mixture. A homogeneous mixture is the same throughout. Okay, is the same throughout. A solution is a homogeneous mixture. It has uniform composition and appearance throughout. Uniform composition. That means only one composition and the uniform appearance throughout. Mixtures of miscible liquids, such as alcohol and water, are solutions. They are the same throughout. Almost all metal alloys, such as bronze, brass, and steel, are solution of one solid dissolved in another solid. Okay, they are homogeneous. Now we know this general alloys. Okay, listed in this table. Bronze. Okay, the main composition is copper. Okay, with some zinc. Bronze. Okay, the main composition is copper. Okay, and other metals in various properties. Okay, including steel. or kind of steel, okay, the main composition is iron, okay, with the different compositions of other elements. Now, for this five material, we learn which is heterogeneous, which is homogeneous. A, scrambled eggs. B, gasoline, or a liquid, okay. Wood, solid. Brass, solid. A pizza, solid. Okay. Now we learn scrambled eggs. Okay. Of course, are heterogeneous because it is with some portions have more egg white than other portions. Okay, the egg white, have the different portion in the different part. So these eggs are heterogeneous. Be gasoline. Gasoline is a liquid, is a homogeneous mixture, okay, having a blend of petroleum-based compounds, okay, that are miscible and consistent throughout, okay. We can mean that is a solution, including or organic liquid, okay. C, wood. Okay, wood is a solid. Wood is a heterogeneous mixture of cellulose, sap, and other materials. Okay. D, brass, of course, is a homogeneous mixture of copper and zinc. Okay, which is the solid solution. E, a pizza. Of course, a pizza is a heterogeneous mixture. Contains flour, oil, water, yeast, tomato sauce, cheese, and other toppings. Okay, of course. Different parts have the different portions and different materials. Now we learn the physical and chemical properties and changes. Okay, learn what is the physical properties and what is the chemical properties. Each substance has specific properties that don't depend on the quantity of the substance, okay? Not depend on the quantity. Properties that can be used to identify or characterize a substance and distinguish that substance from other substances are called characteristic properties. They are subdivided into two categories. Okay, physical properties and chemical properties. Okay, now we know physical and chemical properties are the characteristic properties. Okay, the characteristic physical properties of a substance arose that identify the substance without causing a change in the composition of the substance. Okay, without causing a change in the composition. Okay, color, odor, identify, density, melting point, boiling point, hardness, metallic luster, okay, shininess, ductility, and viscosity, okay, and all characteristic physical properties. Okay, now we learn what is the chemical properties. Characteristic properties that relate to changes in the composition of a substance or to its reactions with other substances. are called chemical properties, okay, related to change in the position, okay. Chemical properties include the tendency of a substance to react with another substance, okay. Characteristic physical and chemical properties, also called intensive properties, okay, okay, are used to identify a substance, okay. Extensive properties of substances arose that do depend on the quantity of the sample, okay. Intensive properties are not, okay. I know the intensive properties, okay, don't don't depend on the quantity of the substance, but the extensive properties of substance, okay, do depend on the quantity of the sample, including measurements of mass, volume, and length. Intensive properties help identify or characterize a particular kind of matter, but extensive properties relate to the amount of matter present, okay, the amount of matter present. Okay, now we learn, okay, classify each of the following as a physical property, chemical property, physical change, or chemical change. Okay, question A, alcohol is flammable, okay. Question B, alcohol is volatile, it evaporates readily. Question C, a sample of table salt, okay, sodium chloride, okay, dissolves in a glass of water, okay. D, question D, over time, a flashlight battery loses its charge, okay, is charged. Now we know, okay, which one is physical properties or physical change, which one is chemical property or chemical change, okay, for the A, for question A, okay, alcohol is flammable. This is a chemical property. Why do we know? We said alcohol is flammable because alcohol reacts with the oxygen in the air to burn produces new substances for water or carbon dioxide. Okay, so this is a chemical properties. Okay, with a change of the composition of the alcohol. B, alcohol is a volatile. It evaporates readily. Okay, we can find for this process there is no change for the composition of the alcohol. So this is a physical property. The alcohol can change from liquid to a gas. It is a change of phases, from liquid to a gas. Okay. Question C. A sample of table salt dissolves in a glass of water. So we know before the dissolve and after dissolve, the table salt, the composition of a table salt and the composition of a water have no change. So this is a physical change. The salt is still present even if the water evaporates. Okay. Question D. Okay. Over time, a flashlight battery loses its charge. Okay, we know. Okay, the flashlight battery. What is the fraction of a flashlight battery. We know, okay, the flashlight, okay, battery, in fact, support the electron energy to the light energy. So if a flashlight battery loses its charge, okay, the electricity is out. Okay, this is a chemical change. Chemical change. Now we learn the law of conservation of mass. Conservation of mass. Okay, when a candle, okay, burns, mass is neither gained or lost. The total mass of the wax and oxygen present before burning is equal to the total mass of carbon dioxide, water vapor, and unburned candle wax that remain after burning the candle. So we can obtain this equation. Mass of wax before the burning, mass of wax and mass of the oxygen is equal to the total of the mass of carbon dioxide, water, and unburned wax after burning the candle. Okay, no total change in mass occurs during the chemical reaction. Mass is observed. Okay, this is known as the law of the conservation of mass, which states that mass is neither created nor destroyed during physical or chemical changes. Okay, mass is neither created nor destroyed. Okay, now because mass is conserved during reactions, matter must also be conserved. Matter is neither created nor destroyed during the chemical reaction. In other words, matter cannot be created from nothing. Atoms cannot be created from nothing. Okay, during the chemical reaction, no atoms are gained, none are lost. Thus, new materials can be made only by changing the way atoms are combined. Okay, only changing the way atoms are combined. Okay, now we learn this example, conservation of mass. Okay, considering the law of conservation of mass, explain how rusted iron, which is iron combined with oxygen in the air can weigh more than pure iron, the weight more than pure iron. Okay, so we use the law of conservation of mass. We can explain this fact. Next, the candle wax burned in the air. So we can explain this fact. As iron rusts, it combines with the specific mass of oxygen. Okay, iron reacts with the oxygen of air. Okay, it combines with some mass of oxygen to produce a mass of iron oxide equal to the sum of masses of iron and oxygen consumed in the process. Okay, so we can learn the mass before the reaction, the total of the mass of iron and the mass of oxygen is equal to the mass after reaction. Okay, the mass of iron oxide. So we learn this fact. Okay, can be explained use the law of conservation of mass. Okay. Now we learn the energy and the chemical change. Energy and the chemical change. So we learn chemical change. Okay. In chemical change, the substance may be changed to other substance, but the atoms are same before chemical change and after chemical change. Now we learn what is the relationship between the energy and the chemical change. Okay, what is energy? Energy can be defined as the capacity to do work, or to transfer heat. Okay, do work or transfer heat. Okay, energy. Okay, energy. So I can learn the exchange of energy have two ways: do work or transfer. Okay, what is work? Work is performed when a mass is moved through a distance. Okay, is a mass is moved through a distance. In fact, we calculate the work. Okay, the equation is work is equals to force times the distance. Okay. Common forms of energy include light, heat, electrical energy, mechanical energy, and chemical energy. Okay. And chemical energy. Energy can be converted from one form to another form. Okay. Each of the various forms of energy can be classified as either kinetic energy or potential energy. Kinetic energy and potential energy. What is the kinetic energy? What is the potential energy? In fact, many forms of energy are the potential energy, especially for the chemical change. Can transferred one form energy to another form energy. Okay, now we learn what is the kinetic energy. Kinetic energy is energy of motion. As a packed automobile. Oh, okay. Automobile starts to roll down a hill. Okay, from the peak to the to the to the okay to the foot, from peak to the foot of a hill. Potential energy is transformed into kinetic energy. Okay, potential energy is transformed into kinetic energy. Mathematically, the kinetic energy, short for Ke of an object, is equal to one half its mass m times the square of its velocity. Okay, like this equation. Okay, like this equation. The unit is joule or kilojoule. Okay. Now we learn what is potential energy. Potential energy is stored energy. Okay, like a chemical change, like a chemical reaction. In fact, chemical reaction transferred by energy. For example, chemical energy to other energy. For example, heat energy or light energy, and so on. Okay, it is energy an object processes because of its position or its chemical composition. Okay, an object possesses, okay, of its position or chemical composition. Okay, during most chemical reactions, the potential energy of the substances involved decrease. Okay, in other words, high energy compounds are usually converted to low energy composed. High energy compounds are converted to no energy composed. When this occurs, energy is released to the surroundings, usually as heat or light, usually as heat. If a chemical reaction that releases energy is reversed, energy must be continued supplied to keep the reaction going. Okay. Like this equation. Okay. If some no energy compounds, okay, absorb some energy, so it can be changed to high energy compounds. Okay, reversely, okay, high energy compounds, if it released some energy, so it changed to the no energy compounds. Okay, this energy can be kinetic energy or potential energy. Now, potential energy stored in sugar and other types of food. Okay, in sugar and some food. Okay, power and so on is released when the food is used by living cells in a process known as metabolism. Okay, sugar combines with oxygen. Sugar, a kind of organic compound, okay, react with oxygen to produce carbon dioxide, water, and energy. Thus, some energy is released as the high energy, less stable molecules of sugar, high energy materials. Okay, sugar. Okay, and oxygen are converted through chemical reactions into the low energy molecules. These molecules is more stable. Carbon dioxide, and water. In this reaction, represented here, energy is released. Okay, released. A reaction that releases heat energy is called an exothermic. Okay, release heat. Okay, a reaction that releases heat energy is called an exothermic reaction. When the term exogonic is used instead of exothermic, it indicates that energy informs other. That heat can also be released when heat or other forms of energy are taken in or absorbed during reactions. The reactions are called endothermic and endogonic reactions. Okay, so we learn endothermic reaction means there is heat to be released into surroundings from these reactions. Okay. I'm sorry. Okay. Endothermic reactions. That means this reaction absorbs energy from surroundings. Reversely, endogonic reactions. That means this reaction released energy into surroundings. Okay. Now we learn from this example, learn energy changes. Okay. As each process listed. Okay. Okay. Here represent a chemical change or a physical change. And is there an increase or decrease in the potential energy of the materials involved? That means for the last state, okay, that a chemical change or physical change. If it is a change, okay, we should explain, is there an increase or decrease in the potential energy? Question A. A glass bowl falls to the floor. A glass bowl, falls to the floor. We learn as the ball falls, the ball will be broken. Before the force or after the force, the composition of this ball is not changed. So we said this statement is a physical change. In this physical change, the potential energy of the ball decreases. Because when the ball falls, some of the potential energy is converted into kinetic energy. So this ball broken. B. A bicycle is pushed to the top of a hill. A bicycle, is pushed to the top of a hill. From the foot of the hill to the top of a hill, we learn it is a physical change. As it is pushed from the foot of the hill to the top of the hill, some kinetic energy transferred to the potential energy. So we know this is a physical change. The potential energy of the bicycle increases as it is pushed up the hill. It is the kinetic energy changed to the potential energy. C. A mixture of hydrogen and oxygen gases explode with a bomb when ignited, producing water. Producing water. We learn, in fact, the gas, hydrogen gas and oxygen gas, all have changed into other substance. So it is a chemical change. The potential energy of the chemicals decreases. Sound and other forms of energy are released as a chemical reactor. So we learn, in fact, the potential energy is chemical energy. After when the reaction, when the hydrogen and reacts with the oxygen, some chemical energy turns into the potential energy. So the potential energy released into the surroundings, such as sound or other forms. D. An electric current decomposes water into hydrogen and oxygen gases. In fact, we learn the water change into hydrogen and oxygen. The composition of the water has been changed. So we learn it is a chemical change. The potential energy of the chemicals, the potential energy of chemicals, water molecules, increases when energy is combined. What is this energy? This energy is electric energy. This is reverse reaction for the previous example. Is a previous reverse reaction for the question C. Question C and question D are chemical changes. Okay. Now we have a break. We have a break for 10. Okay.